Hi guys, today we're going to talk about the pitot instruments. So we're done with aerodynamics, we're moving on to aircraft systems and instruments. And the pitot instruments are a pretty cool collection of instruments, right? They give us information mainly about our altitude, airspeed, right? Rate of climb, rate of descent. So they're pretty important to have, and the way they work is kind of cool. So we will kind of go through the different elements. We'll go through the different instruments themselves. We'll talk about the system as a whole. So, like, what makes up the system besides the instruments? How is the information collected? How does different information that enters the system, affect the readings of the system? And then, if a particular part of the system is blocked or something like that, how does that affect everything? So, let's just kind of dive into it and we'll just talk about it all. So the pitot system, as we talked about, consists of the airspeed indicator, the vertical speed indicator, and the altimeter. We get information about our altitude and rate of climb or descent from the VSI and the altimeter, and then airspeed indicator shows us, well, as you guessed it, right, our airspeed. So how do these instruments get this information, and how do they process it? Well, let's talk about how it acquires that information first. So for all three of the instruments, you will notice that there are linkages to the static port. Okay, and the static port is an opening that is located on the side of the airplane, generally speaking. So for the 152, 172, it's on the left side, and it's like in that front area. So off the left front the cowling up there, the static port is there, and you'll notice that the hole is on the side, so it is oriented in a 90-degree direction from our general direction of travel, right? So about 90 degrees of difference there. And the whole purpose of the static port is to basically just take a reading of the ambient pressure. What I mean by that is just the pressure in the air around the aircraft at that given moment. And that's important when we change different conditions of the atmosphere, right? The most noticeable and appreciable of those different features is going to be the altitude. So as we climb, right, we know that there is less pressure in the atmosphere, and as we descend, there is more. Again, there are some other things that can affect that, but that's the main thing, right? So the static port gives these instruments an idea of our altitude so that all three of these instruments can give us accurate readings. And it's really important for the airspeed indicator to give accurate readings because, as you can see, it's also connected to a pitot tube, which kind of hangs out underneath the left wing on the 172 or 152. And basically, it is an opening that's extended into the direction of the wind that collects air that moves backward. We call this ram air pressure, and it's sent to the instrument. So what I'm trying to say is if we don't have that static port connection, it's not going to do a good job of giving us an accurate reading for airspeed because of the change in air molecule concentration as altitude changes. So static port, pitot tube, there are some things that can happen with these, so the blockages I mentioned a few minutes ago, but there are a few manufacturer kind of fail safes that they put in there to help give us a fighting chance if we have a blockage of either. For the static port, we've got alternate static source. So there's a little red knob, kind of that same color that's on the diagram actually, inside the cabin, and we can pull that out. And what that does is it changes the source of that ambient pressure reading from that static port on the outside of the airplane to the airplane cabin inside. Okay, and the numbers aren't going to be perfect for all three instruments when you change the source of pressure, because believe it or not, that cabin pressure is slightly lower than the air outside. So that means it's moving slightly faster, the air in the cabin. So at least compared to what's collected by the static port, right? None of the other air that's around our aircraft. Okay, but the static port is collecting air at a slightly higher pressure than that of the air in the cabin. So you're going to have a few little errors and everything, but it's again better than nothing, right? Better than having a completely blocked static port. And we'll talk about the implications of having that and having no static air in a little bit. And then for the pitot tube, we've got pitot heat. And pitot heat is technically classified as an anti-icing measure. You can turn it on if you know you're going to be in an area where there are slightly lower temperatures. Um, if you are flying somewhere where there's visible moisture, so maybe you're going in the clouds under IFR, and it's close to freezing, you'll probably have that turned on to make sure that there is no ice accumulation in case the temperature changes. Um, I will say that pitot heat is a little bit more of a preventive feature, so it kind of maybe keeps icing from forming so quickly, but it's not like a de-icing piece of equipment, right? We can't accrue ice on the pitot heat or pitot tube and then turn the heat on and expect it to melt. That's just not how it works. And in any case, right, we should make sure that the weather that we're going to be experiencing is not going to have icing form on the aircraft, right? Sometimes we can't help that because conditions change, but we should do everything that we can as pilots to make sure we will not accumulate icing, right? Because icing is detrimental no matter what type you get. It affects the aircraft negatively, okay? And then the other thing we have with the pitot tube is the drain opening in the back. This is more so a feature for, say, if you're flying through rain. It gives the water that enters the pitot tube a chance to exit out the drain opening. It is a hole in the back, so as that air moves in, it does have that tendency to kind of move usually up the tube. But the other air that does not go in the tube that goes around it, especially that air that goes under it, has a high velocity, right, compared to probably what's already in that pitot tube. So basically, it kind of creates a little bit of a low pressure area and just brings that water out, right? So it kind of suctions it out so that it's not interfering with the reading. Okay, so that's kind of the overall composition of the pitot-static system. Let's talk about the instruments and how they work. So the altimeter is the first one I would like to talk about because it's the easiest really to explain. We've got the casing itself, right, that's sealed to a degree. You can see that the only opening to the outside is really the static port, right? You've of course got the face that you're familiar with that shows your respective altitude. You've got different types of pointers to reflect different magnitudes of altitude. So you've got the 1,000 foot, right? You've got the 100, you got 10,000. Okay, 10,000 usually isn't something that we care too much about because we're not really going to be going up that high. I think the 172s have a service ceiling around like 12,000. So I mean, yeah, we might be a little bit above 10,000, but it's not really worth it. Okay, and then of course the adjustment window out front, right? You can see that the knob we use to change the altimeter setting or the pressure setting is linked mechanically to the rest of the gears and everything. So we're basically just changing that whole relationship to reflect the current pressure that is reported. So in a nutshell, the altimeter works via a differential in pressure, right? So this stack of aneroid wafers is sealed to a certain pressure. Some people say it's standard pressure. Honestly, I think it's just a pressure, right? They just seal it to a pressure, um, and it basically stays, right? The pressure inside stays. It's not going to go out, right? Think of a sealed bag of chips. It's not going to exit, right, until we open that. But hopefully these aneroid wafers never open. Okay, and then pressure from the outside, the ambient pressure, right, goes inside that static port opening and then fills that casing around there. So the altimeter shows different altitudes based on that differential of pressure between the casing and the aneroid wafers. So if we are climbing, right, then remember the pressure in the atmosphere is decreasing, right? So if we have less pressure in the surrounding air, the ambient air, then there's less pressure entering the casing. And if the pressure inside the aneroid wafers remains the same, due to Boyle's law, we will have expansion, okay, increase in volume of the aneroid wafers, right, because the pressure around the wafers has gone down. You might see, I used the example of a potato chip bag. You might see people doing that from time to time, right? Is if you go flying and you take a bag of chips with you, let's say you brought it on sometime after security, right? And I guess it doesn't work so well in a pressurized aircraft, but if you're in like an unpressurized aircraft, if you brought a bag of chips with you, right, on the ground, it would have some give to it. We would have to squeeze it quite a bit to get it tight to the point where it would pop, right? So there's a little bit of space in there. There's not a ton of pressure, okay, inside there. And the volume is small, right, because the pressure on the bag is great, okay? But if we ascend in the atmosphere to a point, right, we know that the ambient pressure goes down. And the further down it goes, the less pressure is exerted on that bag of potato chips, and we have expansion of that bag, right? It gets to the point at some point where it's just completely inflated, right? And that's not because there has been a change of the amount of air inside the bag or the pressure of the air inside the bag. That is sealed, so it's going to remain the same. It's the fact that the pressure on the outside has um, decreased, right? So less pressure surrounding it, the larger the thing gets. So that's what's happening here inside the casing. Okay, so if we're climbing again, like I said, then the pressure in the casing goes down, allowing those aneroid wafers to increase, not because the pressure inside the wafers has increased or anything, it's still the same, but the surrounding or ambient pressure has decreased. And that causes the linkages to move and causes the pointer or the arms to show an increase in altitude, right? And then once that static port pressure reading remains the same, then there is no more change, right? That shows that we've leveled off because there is no change in that pressure. Therefore, the aneroid wafers are not changing size. If we are descending, right, we know the pressure in the atmosphere overall is going to increase. So the reading that the static port takes feeds an ever-increasing pressure into the casing, right, which causes the aneroid wafers to get smaller and smaller because that force that is pressing on them is getting bigger, right, because there's more pressure, and that causes those linkages and gears to move the arms to show a decrease in altitude. And then once we level ourselves off, right, there is no longer that change in pressure, that increase. So the arms stop moving because the aneroid wafers are not changing size anymore. So that's all it is, right? It's just changing changing pressure in the casing. It changes the size of the aneroid wafers. The VSI is a little bit more of a, I guess, harder conversation, but in principle, it's almost the same. The major difference here, there's a couple. The first is the fact that we do not have a stack of aneroid wafers anymore. We now have a diaphragm, and the diaphragm is not sealed. Okay, so the pressure inside the diaphragm can change as well as that of the casing. And then we've got two different connections that run from the static port, one to the aneroid wafer and one to the casing. Okay, so with those things in mind, it would seem that that makes no sense, right? Because if the pressure in the diaphragm, let's say we're initiating a climb, if the pressure in the diaphragm decreases, then the pressure in the casing would also decrease, right? So like there's no pressure differential. So how would this thing show us any information? Well, we have to consider the fact that the linkage to the casing is a calibrated leak, which means that it takes a few seconds for that new pressure reading to fill that casing. Whereas with the diaphragm, it is a direct linkage, okay? So as soon as that pressure reading of the ambient pressure from the static port changes, the pressure inside the diaphragm is changing. Okay, but with the calibrated leak, it takes a few seconds for that calibrated leak to reach that new pressure, okay, for the casing. So with that in mind, now we can kind of piece together how this VSI works and shows us our rate of climb or descent. If we are, let's say, climbing, we know that the ambient pressure decreases. So the pressure that enters both the calibrated leak area that goes to the casing and both the direct connection to the diaphragm, both those pressures are decreasing, right? So if our pressure decreases in the diaphragm, then we know we're going to have more expansion, right? There's less pressure in there. I'm sorry, we're going to have contraction, right? It's going to get smaller, okay? And at that particular moment, because that calibrated leak takes a few seconds to equalize, right, we're going to have a slightly higher pressure inside that casing area than the diaphragm. And this difference in pressure causes a reading to be shown. So anytime the pressures are not the same between the diaphragm and the casing, in this case the casing has a higher pressure than the diaphragm, it will show a climb, okay? And the greater the pressure differential, the greater the rate of climb, right? So if we're changing altitude super fast, we're climbing at 1,000 feet per minute, you got to understand that that pressure is changing quickly, right? It's changing instantaneously in the diaphragm, but it takes time for that casing to catch up because of the calibrated leak. And then consequently, if we're descending, right, we know that our pressure increases as we descend in the atmosphere. So the diaphragm, again, is going to immediately reflect that new pressure, right, as we descend. So what's going to happen is the pressure inside the diaphragm is going to continuously increase as long as we descend. And then that pressure in the casing is also going to continuously increase, but it's going to be running a few seconds behind, which means that the diaphragm has a higher overall pressure than the casing. And anytime the diaphragm has a higher pressure than the casing, we now have the linkages moving the arms to show that we have some sort of rate of descent. Okay. So depending on which way that disparity goes, the arms show either a climb or a descent. And then once we level off, right, if we're climbing or descending, once we stop that and we level off, after a couple seconds, when that calibrated leak finally catches up, then the pressures between the diaphragm and the casing equalize, right? And when they are equal, they show zero. And that makes sense, right? We're not climbing or descending, so there should be no significant changes in pressure between the two. So I hope that makes a little bit of sense. I hope that explains that. I've got a little bit more information on this slide about that, what we basically just talked about, but you can read that on your own time. Okay. So when we talk about the airspeed indicator, we have to kind of break down the atmosphere a little bit further. We've already kind of talked about how that pressure change happens, but we need to kind of fit this to the mold, the context of the airspeed indicator. So the airspeed indicator has a link to both the pitot tube and the static port. The linkage to the pitot tube is probably the most reflective of what our actual airspeed is. However, because of the pressure change in the atmosphere, we can't rely solely on that ram air pressure reading to generate an accurate airspeed. For instance, if we did not have a linkage to the static port to give us information about the ambient pressure at any point, we would have, let's say we're actually doing 100 knots, right? We have somebody in another airplane who has a radar gun and they're measuring us at 100 knots, right? So if we're at 3,000, right, excuse me, we know that we have a decent amount of air molecules concentrated in the air because we are at a lower altitude. And what this means is as we move through at 100 knots, right, our ram air pressure would be quite strong because it would be picking up a decent number of air molecules. However, if we climbed, right, to let's say 10,000, okay, and we were up there and we got our speed up to 100 knots, right, via that other person's radar gun from the other airplane, right? They're showing us at 100 knots. We would actually be reading an airspeed a lot lower than 100 knots because the concentration of air molecules is not as strong. So because there's less air, that ram air pressure is a lot smaller, right? It's not as great a pressure force, okay? So the link to the outside via the static port, right, to pick up that ambient pressure gives us that missing piece, right? It allows us to account for those differences in air molecule concentration so that if we're at 3,000, that higher ram air pressure can also show us 100 knots, right? And if we're at 10,000 feet and that lower ram air pressure is collected, right, it can also show us 100 knots, okay? But it all has to do with the fact that the ambient pressure is used as an adjustment, okay? And the crazy thing is, I just pulled those altitudes out of my head, and I wasn't even looking at the slide. I just kind of like talk, right? Just kind of stream my consciousness into this, and here it is, 100 knots, 3,000, 10,000. So I definitely made this, right? Kind of reminds me. Okay, so let's think about it in another way too, right? If we were Actually, no, let's not do that. Let's just leave that thought process at that. Let's continue to the next slide to just kind of think about it mathematically, right? So as we talked about, the airspeed indicator has linkages to both that pitot tube and the static port. And the linkage to the pitot tube goes directly to a diaphragm. So the more ram air pressure there is, the greater in size this diaphragm becomes, right? And that is our ram air pressure, right? It's measured via that. And then our static air line goes into the casing surrounding it. That kind of makes that adjustment that we've talked about, right? So anytime we have more ram air pressure, we will increase our airspeed for the most part, because you can see that the linkages are set up to reflect that. But let's make this math really quickly, because sometimes this is a really hard concept to understand, right? So our ram air pressure, remember, is most of what our airspeed indicator shows us. Generally speaking, the more ram air pressure there is, the greater the airspeed registered will be. But we have to have that adjustment factor to account for the fact that the amount of ram air at different altitudes is not the same, right? If we travel at the same airspeed at 10,000 and 3,000, we will definitely pick up a higher ram air pressure at 3,000, right? Because the concentration of air molecules is that much greater. So when our static port picks up that ambient air pressure, right, we basically subtract that from our total ram air pressure to create a dynamic pressure. And the dynamic pressure is whatever our airspeed indicator shows us. Okay, so if you think about it this way, right, at 3,000, we would have a much higher ram air pressure, but also the air pressure picked up by the static port, right, is going to be higher because we are lower in the atmosphere. So there is a larger adjustment because we have that much more ram air and we're lower, right? So high ram air pressure minus relatively high ambient air pressure gets us a dynamic pressure. Whereas if we were to climb to the 10,000, right, and achieve the same airspeed, we would have a smaller amount of ram air, right? Because there are less air molecules. Even though we're moving through the air at the same rate, there's just less to pick up. So there's a smaller ram air pressure, and then the ambient air pressure that the static port picks up is also smaller than it was at 3,000, right? Because that pressure has decreased as we've increased our altitude. So a smaller ram air pressure reading minus a smaller ambient air pressure reading equals the same dynamic pressure, right? So if we have a higher ram air pressure, there has to be a greater adjustment to reflect an accurate airspeed at lower altitudes. And at higher altitudes, because there's less ram air pressure, there has to be a lower adjustment to reflect the same dynamic pressure. I hope that makes sense. Okay? So that adjustment's got to be correct. If it's not correct, we're not going to see the correct airspeed displayed. Okay? So I hope that's insightful. I think that was a little bit better than what I did in class. My explanation was kind of janky in class, but hopefully that's a little bit better to illustrate that fact. Okay, and here's more information on that, right? So let's just walk through a scenario. Let's say we are level in altitude, right? We're not going to consider that factor right now. But let's say we are decreasing our airspeed. We're slowing down for the purpose of a maneuver. So we take out some power, and as we slow down, what happens to that ram air pressure? It decreases, right? No matter what the concentration of air is, if we move through it at a slower rate, the pressure of the air is going to decrease, right? Or at least the ram air pressure that the pitot tube is picking up. Okay, so that's going to go down. But if we are maintaining a constant altitude, right, that adjustment that static port is picking up in terms of ambient air pressure is not going to change, right? So if we were, let's put ourselves at 3,000, right, to go with the example that we've talked about this entire time. If we decrease our power at 3,000, right, we know that our ram air pressure is going to decrease. And before, when we were at 3,000, remember we had a relatively high ambient pressure adjustment, right, because there was a higher amount of ram air. But we've decreased the amount of ram air without changing the adjustment. Less ram air minus a relatively high ambient pressure reading equals a lower dynamic pressure than we had before, right? If the dynamic pressure is less than we had before, we will see a decrease in airspeed on that indicator. Conversely, if we add a lot of power to increase our airspeed, right, make sure we have enough forward pressure to make sure we don't climb away. But again, maintaining that 3,000, if we increase that power and maintain our altitude, then our rate of travel through the air is going to increase, and we will pick up a higher ram air pressure. Okay, and as we pick up that higher ram air pressure, that's going to increase that side of the equation. Our adjustment factor is not going to change because we aren't climbing or descending, so that ambient pressure collected by the static port will be the same as it was before at 3,000, because we're still at 3,000. So a higher ram air pressure minus a relatively high ambient pressure equals a higher dynamic pressure. Okay, and when we boil that all down, we can say that a higher dynamic pressure creates a higher indicated airspeed. Okay, so it will show us that we're moving faster because that dynamic pressure has increased. So depending on what you're doing, different parts of that equation change. If you are changing your actual airspeed or rate of travel through the air, your ram air pressure will increase or decrease. Okay. If you are changing your altitude, then both those values will increase or decrease, right? So if you go to a higher altitude or you are climbing while you are accelerating or decelerating, then that's also going to affect that, right? So that adjustment factor, if you're climbing, that's picked up by the static port is going to decrease. If you are descending, that adjustment factor is going to increase. And also your amount of ram air will also reflect that change as well, right? If you're climbing, the amount of ram air collected will be decreased, right? Part of it is a matter of angle too. Initially, when we start the climb, it's not a great angle for that pitot tube to collect the air, and then once we've kind of established ourselves in the new flight path, it's a direct kind of angle for that ram air collection. But that's another discussion for another time. But that's going to affect, all those things are going to affect the amount of ram air that comes in. Okay, so what we're considering at the end of the day is once we know what happens to the amount of ram air, once we know what happens to that ambient pressure reading, what is that dynamic pressure? Okay, is it higher than it was before? Is it lower than what it was before, or is it the same, right? And when we have changes in that dynamic pressure, we have changes in our displayed airspeed. Okay, so hopefully that was insightful and better than I did in class. Let's talk about blockages next. So we learned about the beauty of having those openings for those different instruments to show us different things. But if we don't have those openings available to collect those pressure changes, then the instruments can't accurately reflect those changes, right? So it's not like we do anything to purposely block them or anything, but things that we encounter during flight can sometimes get in the way. So if it's raining, you might have water that blocks those entrances temporarily. For the pitot tube, it's not that big a deal because that water goes in and goes out that drain tube. But for the static port, sometimes you have water that attacks the front of the cowling and streaks back, and sometimes it will intermittently um, close off that opening over the static port. So it's not a big deal in level flight, but I know I've gone on one instrument flight where it was raining kind of hard. And what happens when you're trying to descend is, let's say we're starting at 3,000 and we want to get down to like 2,000 because ATC told us to. You will reduce the power and initiate the descent. And you will feel like you're descending because you are. But if there is water covering that opening, your airspeed indicator, I'm sorry, your altimeter will not show you immediately that you are descending, right? So it'll show 3,000 for a little bit, and then once that water goes away and the opening is clear again, It might show you 2,800 or whatever, depending on how fast that water's moving. And it just kind of does that. It just kind of jumps down until you get to where you need to be. So that can happen, right? You can have bugs if there's a poor critter that's in the wrong place at the wrong time. They can get jammed in the pitot tube. And then icing, right? Hopefully that's something that we just don't have to tangle with, but it is a thing that people run into. And we have some protection from that, right? We've got the alternate static source, and then we've got the pitot heat. But again, those aren't absolutes, right? They're not completely reliable and don't erase the fact that we are having to deal with ice, right? There are some aerodynamic things that we have to deal with, and the readings that are collected by the instruments are sometimes still not 100% correct. They still exhibit some error. So those are nice things that the manufacturer has left for us, but it's also important for us to know what happens when we have blockages, right? What these instruments are going to show us, even though they're not correct. Because sometimes figuring out that you do have a blockage is seeing that these instruments are not behaving the way that they're supposed to. For instance, if you are in the airplane, right? If you're sitting there flying the airplane, you can look out and you can see the pitot tube, right? But when clear icing happens, you might not be able to see that it's iced over, right? Um, or the static port, right? You can't see that at all. So you can't really look and see what's happening with that. You don't really know. And sometimes, or most of the time, the first indication you have that something is out of whack is when the instruments aren't showing you what you're expecting them to show you. Okay. Um, I think I heard a story once of somebody who forgot to take their pitot tube cover off, and they got as far as the runway, and they didn't realize it yet, but they were expecting that airspeed to start registering because they were moving fast enough to the point where an appreciable amount of ram air pressure could be collected by the pitot tube to register that reading, and it just never happened for them. And then they looked out and they saw that the pitot tube cover was still on there. Okay, so be careful in the pre-flight. Make sure there's nothing that is blocking that pitot tube. Make sure it's open and unobstructed. Otherwise, you will not get the expected airspeed readings. Same thing for the static port, right? Try not to touch the static port, but make sure it is open. If it's blocked off, then I would say don't fly, right? Okay, so let's talk about static port blockages first. The reason why I want to talk about these to begin with is the fact that all three of the instruments are connected to the static port. You're going to see some different things happening to each of them. And if you see these three things happening, then you know that you've got a static port blockage, right? And you can go ahead and pull that alternate static source. So when we don't have an opening out to the ambient air pressure anymore, right? If there's, let's say, icing that covers that static port opening, then there is no way to dispel the pressure that is already contained in the system. So whatever pressure was last collected by the static port is locked into the system, right? That's the pressure that's fed to all three instruments and is not going to change until that blockage goes away. So if your altimeter is I guess if you've got the static port blockage, right, your altimeter will remain kind of normal seeming to you if you do not change altitudes. The place where most people figure out they have a blockage is when they change altitudes, right? Because we should expect that ambient pressure to change, and it does, right? Outside the aircraft, it does. But changes in ambient pressure usually means that those instruments are going to yield a different reading from what they're showing you. But if you have a static port blockage, remember all that pressure that's already in the system is locked in, right? It's not going to be able to reflect those changes in ambient pressure. So what happens is your altimeter will just continue to show you the altitude where the blockage occurred, right? Whatever pressure is in there to reflect that particular altitude. So, I mean, at least you know where the blockage occurred, right? At least you have that information. So that might be something to write down or record before you pull that alternate static source, right? So you know where the blockage happened, so you know which altitude you should probably not go back to for like icing, right? That's too high, okay? So altitude is going to freeze. The VSI right? If we think about the nature of the VSI, we know that the diaphragm and the casing are designed to reflect different pressures when the ambient pressure outside is changing, right? The diaphragm immediately reflects the pressure outside, while the casing is a few seconds behind, right? So anytime there's a disparity in those pressures, the VSI reads a climb or a descent rate. If we've been at level flight, right, then the pressure between the diaphragm and the casing should be equal, okay? If you start to descend and you see that your VSI is not generating a rate of climb or descent and it's just showing 0, then that also leads the pilot to believe that there has been a blockage, right? Because the pressures are equal between the two because whatever pressure was in the system is trapped in the system. So there's no change in pressure that would lead to a disparity in pressures that would yield a reading. Your VSI is going to show you 0, your altitude is going to be frozen at the altitude of the blockage. Your airspeed indicator is kind of a special one to think about, but let's like put on our thinking cap for a minute here, right? So we said that the purpose of having that static port connection to the airspeed indicator is to oh, I should change slides too. I'm sorry, I'm just talking, guys. So the purpose of having that static port um, connection, right, to the airspeed indicator is to account for that change in ambient air pressure, right? So we know how big or small that adjustment needs to be so that we can get the correct dynamic pressure, right? If we have a blockage happen at a certain altitude, let's just make it 3,000 again for convenience, right? If we have a blockage happen at 3,000 and we descend below 3,000, we know that the ambient pressure increases around the airplane. But if we have the blockage, right, then there is going to be no ambient pressure increase inside the system. Okay, so if that pressure can't increase to make that bigger adjustment as the ram air increases, right, because we're descending, so there's more air molecules, if it can't make the increasing adjustment, right, the larger adjustment, then it will not be making enough of an adjustment, okay, for that. So what will happen is the ram air pressure will increase, but the ambient pressure will not, and that leads us to have a dynamic pressure that's a little too high to reflect an accurate airspeed, okay? And this all, again, assumes that we haven't changed our airspeed at all. If we pull back the appropriate amount of power to kind of maintain our airspeed in the descent, that's what's going to happen, right? Even if you leave the power as it is, right, and descend, your airspeed you would expect it to increase, but it will increase at a rate greater than you are expecting. Um, if you pull back your power so you can decrease at a slower rate, so you pull a lot of power out, so you slow down your airspeed, it's still going to reflect an airspeed higher than it should. Okay, and that's just again because it's not making the right sized adjustment. So ram air pressure is increasing, but that adjustment just can't increase because of the blockage. So we have a higher overall dynamic pressure. If we tried to climb, right, the opposite would happen. So because we are climbing, right, that is less ram air that's collected. It doesn't matter if you're speeding up, right, it might keep that ram air pressure the same for a little bit, but I don't imagine you would be speeding up for a climb. You would likely be slowing down or maintaining a constant airspeed. So in those cases, because we are climbing, right, there's less air molecules just floating around in the atmosphere, right, because there's less pressure. So the ram air pressure goes down, but the adjustment can't change, right? That ambient pressure that the static port collects can't change. It's locked in at whatever it picked up at that lower altitude. And because it is a lower altitude, right, that ambient pressure is higher than it needs to be if we are climbing, right? So in that case, we have lower ram air pressure and still a high ambient pressure adjustment, right? It's too high, in fact. So because it is too high, then your dynamic pressure will not be strong enough to reflect an accurate airspeed. Okay, it's going to show you an airspeed that is slower than what you are actually doing. Okay, so that's how I think about that, right? And in class, I talked about taxes and things like that. If the adjustment, so let's say that ram air pressure is us, right? We make all this money every single year, and then the ambient pressure, the static port opening, that's going to be the IRS or the government. Okay. Um, if we're all to live in a fair and equal society, right? Depending on how much money we make or how much RAM air is present, right, there should also be an appropriately sized deduction, right, or taxes imposed, aka ambient air pressure, right? So if we make more money, so if there's more RAM air pressure when we're climbing, or I'm sorry, when we're descending, right, there should be more of a, we should be in a higher tax bracket, right? So they should make a bigger adjustment to keep everything fair. However, if we're climbing, so the ram air pressure decreases, so we take a pay cut, we're making less every single year, then I'm pretty sure we would all be very upset, right, if the government didn't make that adjustment correctly, right? If they left it higher than it should have been, like where it was before the pay cut, we would not be happy, right? So that adjustment factor should be smaller to create that fair tax implementation, I guess you could say, right? So think of it in that way, right? We should have kind of the same-ish dynamic pressure at the end of the day. So like our take-home pay. Um, I mean, that's obviously not the case, right? We've got people who make a ton of money and people who don't make so much, but at least the government doesn't just charge one flat rate for taxes. They try to be fair about it. I mean, taxes are they suck, right? They're not good, but the government tries to be fair in the amount that they take off based on how much you make. So you can think about that adjustment factor in that way as well. If we talk about the pitot tube blockage, we know that the pitot tube only affects one of our instruments, right, the airspeed indicator, and this is where that ram air pressure comes from, right? So we have a couple different stages of blockages to talk about for the pitot tube. So stage one is the most simplistic. The opening to the pitot tube is blocked, so that front opening is blocked. So let's say like a bug jams itself in there. We got like a bumblebee flying at like 3,000, which is like not going to happen, right? But it jams its big old self into that pitot tube opening. The drain hole in the back is still open, so while the pitot tube can't collect any more air from out in front because that bumblebee is like closing up that opening, air can still leak out of the system. So unlike that static port blockage we talked about before, air still leaves the system, right? It leaks out that drain hole because that air that's rushing past the pitot tube, right? Because it's moving faster than the pressure that's stopped up inside it, right? It's a low pressure area. Inside the pitot tube is a high pressure area. So the high wants to seek the low. So it's basically going to vacuum out all of that pressure inside the pitot tube. So if there is no ram air pressure, what does our airspeed read? Zero over time, right? It reads zero because you have to have some ram air pressure, right? You can't just have ambient pressure for the airspeed to be read. You have to have ram air pressure, and we know that the airspeed starts to come alive when the ram air pressure is slightly greater than the ambient pressure outside, right? If they're equal or the ram air is less than the ambient pressure, we don't have an airspeed reading, right? But as we accelerate down the runway, we are speeding up and collecting more ram air in that pitot tube, and the more we have, the faster that airspeed gets, right? Um, so that's what would happen if we still had that drain hole open. It would all just bleed out, and the airspeed indicator would read zero. If we have both the front and the drain hole blocked, then it is very much like that static port blockage in the sense that no air is leaving that system, right? That pressure reading is going to stay the same the entire time the blockage is happening. So if that reading can't change, then the ram air is stuck in the system, right? And the only variable that can change now is that ambient air pressure that makes that adjustment, okay? So if we had, again, at 3,000, if we had a blockage happen, right, and we had a decent amount of ram air, and we have the blockage happen, that ram air value is not going to change, right? But if we start climbing ourselves, then the thing that will change is that ambient air pressure that's brought in from the static port, and that will start to decrease. And that overall, if we have the same ram air pressure and less of an ambient air adjustment, right, that leads to a lower dynamic pressure overall. So if we have I'm sorry, I'm getting my math wrong. If we have the same amount of ram air and a smaller adjustment, then that leads to a higher dynamic pressure. So as we climb, our airspeed will go up because there's less of an adjustment being made, right? Or what the airspeed indicator reads will go up. Our airspeed will likely go down, right, if we're climbing, but our airspeed indicator will show a higher value than what we are actually traveling at. Conversely, if we descend, right, again, the ram air is not changing, but as we descend, right, that static port is picking up a higher ambient pressure, right, the lower we go. So there is a greater adjustment being made. So same amount of ram air pressure minus a higher adjustment for the increasing ambient pressure equals a lower airspeed displayed, right, a lower dynamic pressure. So as we descend, our airspeed would show a decrease. Now, the other way to think about this thought process is the fact that the only opening that is allowed to change its pressure reading collected when we have a pitot tube blockage is that static port, right? So think about the altimeter. That is also only opened up to the static port. So in essence, our airspeed indicator functions like an altimeter, right? Because as we ascend, there's a smaller adjustment happening over the same amount of ram air pressure, right? So higher dynamic pressure, and our airspeed goes up just like our altitude would, or does. And then as we descend, right, there's a greater adjustment being made for the same amount of ram air, and our dynamic pressure decreases along with our displayed airspeed and altitude. Okay, so hopefully that's helpful to piece it all together. And then if everything is blocked, right? If no openings are available, then man, I'm sorry, I'm just talking. I have my eyes closed. I'm just formulating everything in my brain, so I apologize for not changing the slide for you guys. But if we have a blockage of all of the openings, so static port blocked, iced over, let's say pitot tube iced over in the front and back, everything is going to stay where it's at. It's not going to be able to change, right? So whatever your last airspeed was is what the airspeed indicator is going to read. Whatever your last altitude was is is what the altimeter is going to read, and then your VSI is again just going to show you 0, right? So if you have that blockage completely, and you haven't applied the alternate static source, then that's what's going to happen. Okay, but if you pull out that alternate static source, then at least you've got a fairly decent and fairly correct measurement of the ambient air pressure, right? Again, like I said, it's slightly lower in the cabin, so your altimeter is going to read slightly higher, okay? And then initially when you pull that alternate static source out, let's see, the pressure in the diaphragm is immediately going to be lower than that of the casing. So when that happens, right, it's going to show a climb for a second, okay? And then it'll kind of revert back to equal. So at least you've got those instruments working fairly normally. Airspeed, I would say disregard. I would say go off of the aircraft sounds, right? You still have your attitude indicator. You can still look outside and all those things. So just pitch for a normal pitch attitude, right? That would yield safe flight. And then just use your power reading, so your tachometer and your ears to just kind of keep track of your airspeed. It's always good to be a little faster than slower if you aren't sure of your airspeed, if it can't be displayed. That way you've got a little bit of a cushion, right? Because we know that stalling happens more often when we are on the slower side of things, because we're trying to make up for that loss of lift with the increase of angle of attack. Okay, so that's kind of how I would handle that. Um, does anybody, or why am I asking if you guys have questions? If you have questions, you know what to do. You know where I am. I can't hide from y'all. So come to my office if you have questions. Ask me next time in class I see you guys. Send me an email, send me a text, whatever you guys need. Okay.